Any questions about anything at all before we get into new stuff today? All right. Well, this next chapter is basically trying to get us into trying to set us up for statistics stuff that we'll be doing, well, that we don't necessarily do it, but we do it in another class. We'll touch on it briefly in the next chapter, but we just need to get us set up to be able to do that extension later, right? We need to be able to build up to that point. So with that in mind, we're going to talk about what are we referred to as bivariate distributions. Your book does discrete bivariate distributions in section 1, and then does continuous bivariate distributions in section 4. We're going to do them all at the same time. Okay. So we've already talked about discrete probability distributions and continuous distributions, so I don't know why we've split them up into two. So I'm not going to. All right. So there are times where you might have probabilities associated with two random variables, and those two random variables might interact with each other. To give an example, perhaps you've got a student's ACT score and a student's freshman GPA in college. Okay, those would be two, you can think about it as random variables, but they might have some relationship between them, right? So statistics, a lot of times, is investigating what is a relationship between two variables that perhaps have some relationship. And we'll talk a little bit about how we might measure such a relationship later on today as well. All right, so this is kind of the motivation for why we start with bivariate distributions. Later on, we'll talk about multivariate distributions where you have several random variables and not just two. Okay. But we'll start with bivariate because that kind of makes sense. If you have one to start with, and we've done some analysis with those things, let's just bump it up one level rather than, a whole bunch of levels all at the same time. All right. Pardon me. So to that end, let's talk about how we get a joint PMF, either from a PMF or PDF, either or, depending if you're talking about discrete or continuous. So we'll let X and Y be two random variables. Defined on some sample space. All right. So this sample space needs to represent outcomes for X and Y at the same time. So your sample space here is going to be thought of as ordered pairs in this case. Okay, we need an outcome. We need an outcome for X. We need an outcome for Y, and they need to be able to happen at the same time, right? So we'll have a sample space that's made up of ordered pairs. Your books refer to it as a two-dimensional space. Okay. Then a joint probability mass function or we could replace the mass with density in the continuous part. Okay. If they're continuous random variables, we'll have a joint probability density function versus a mass function. Okay. Oops. I'm just not writing this very well. There's going to be a function with domain S to the real numbers. I should say the non-negative real numbers. Now, that's even better. To the interval from 0 to 1, because we certainly don't want anything to be between 0 and 1, less than 0 or greater than 1, so that when we take our sum of our f of xy, we'll use f of xy to denote it in both cases, the sum over all possibilities We'll write it in this fashion. Notice in this case, we're doing a double sum if it's in the discrete case. This is just saying sum it all for all the possible x's and all the possible y's that you could possibly have. So all the possible ordered pairs is written this way. So we take the sum over all of those possibilities of the function. What better we get if this is going to be a probability mass function or a probability density function? What should we get? 1, good. Okay. If I change this to a continuous distribution, what's your double sum going to change into, do you think? Double integral, yep. Just like it did for the continuous case, right? We'll change our double sum, will change into a double integral. And if A is a subset of S, then the probability that our xy is in A will be the double sum over S of f of xy, just like we did before. Or we'll do the double integral over A. Oops, dA. Okay. Either we'll do it with a double sum or we'll do it with a double integral. Okay. And then you can probably naturally see how we would do trivariate distributions if you had 3 random variables or multivariate distributions. We keep getting higher. This is the same definition we had for probability density or probability mass functions before, correct? Not any different? Okay. So let's see if we can put this into practice. Let's look at this first problem. First problem here is we got one random number being selected from the even integers between 0 and 8, and then another integer selected from between 0 and 4. X is the integer selected from the first, and y is the sum of the 2 integers that were selected. Okay. So the first thing it asks you to do is basically make a sketch. Say that again. Name of a what distribution? There isn't a name for this distribution. We're just making it up. We're just making up an example. There is no name to put on it. Okay. All right. So the first thing it's asking you to do is when it says show the joint PMF on the space, what it means that we're going to do is we're going to sketch the sample space. In this case, our sample space will be dots because it's a discrete distribution. Okay. And then when it says show the joint PMF on there, we're just going to put the probabilities associated with each of those dots just next to the dot. Okay. It'll make more sense when we get to that point. Okay. All right. So if I have my distribution, my x can take on the value, and I'm just going to go by 2s. Your x's can go 0, 2, 4, 6, or 8, right? If my use the horizontal axis to represent my x-axis here, those are the values that I can have for x, right? Plus the 0, it could be on the y-axis. On the y side, what are your possible values that you can get? 0 up to 12, right? Is the biggest one we can get? Good. All right, so all right, so now let's actually go through and see what sums we can get. Well, the only way to get a sum of 0 is to use 0, right? Oh, I'm sorry. No, it's okay. We're okay so far. All right. The only way to get a sum of 0 is a 0, right? we can get a sum of 1. How do we get a sum of 1? Well, the x had to be 0, didn't it? And we had to pick a 1 out of the second set. Okay. How about a sum of 2? Good. So the y can't, the y is the sum, right? Because the y is represented. Yeah, okay. So the way we get a sum of 2 is that the x was 0 or the x is 2, right? We agree with that? It's the only way to do that. How about a sum of 3? The x is 2, or the y is, the x is 2 or 0, right? Those are the two possibilities for that one. Remember, y here is representing the sum, not the value we're picking out of the second set, right? The y here is the value out of the random variable. It says the random variable is the sum, right? Okay. Okay. How about a sum of 4? How can we get that? Well, either the x has to be 0 or a 2 or a 4, right? Agree with that? Okay. A sum of a 5. So yeah, we use a 0 and a 2 or a 4, right? For the x's. Because I could use, you can't use the 0. Good. Oops. Just erased my whole x-axis, or my whole y-axis there at the same time. Yeah, we can't use a 0, can we? It has to be a 1 and a 4, or excuse me, a 2 and a 2 and a 3, or a 4 and a 1. Okay. For a sum of 6, can we use it? We can't use 0, but we could use 2, 4, and 6. For a 7, four and a 6, good. For an 8, 4, 6, 8. For a 9, 6 and 8. For a 10, 6 and 8. For an 11, just the 8, and for a 12, an 8, right? There's a little bit of a pattern that's going on here, right? We got 5 dots stacked on top of each other as you move across, right? Are we okay with how we got the graph? All right. So then when it says short, I'm not going to write all of these in here in this case. We will do the marginal one, and I'll talk about what the marginal is here in a second. For the joint PMF, though, each of these variables each of the numbers were randomly selected, right? So for each of these dots, what would be the probability associated for each one of them? For example, to get this dot right here, we had to pick 0 and 0, right? To get this dot, we had to pick 0 and 1. This one we had to pick 0 and 2. This one we had to pick 2 and 0, and so on up the line. Okay? What would be the probability associated with each of these dots? 1 over 25. Yeah, exactly. Yeah, it's 1 over 25, right? There's 5 ways to choose the first number. There's 5 ways to choose the second number. So for any particular pair, it'd be 1/25th, right? Okay. So when it says sketch the PMF on this one, it really would mean that on each of these dots, I'd put a 1/25th next to it. I'm not going to write it for all 25 dots because that's going to get really repetitive. Okay. But if I were to actually sketch it on there, I would need to write the 1/25th out for each single one. Okay. That process okay? All right. The next part says compute the marginal PMFs. And the idea that where it gets its name is what we're going to see that here in a second about how we're going to represent it on the graph. So what the marginal PMF means, or marginal PDF, depending on if you're talking about discrete or continuous, basically just means what you would expect it to mean. In the discrete case here, your possibilities for x are 0, 2, 4, 6, and 8. Your marginal PMF would be, what's the probability that x is 0? What's the probability that x is 2, 4, 6, or 8, right? And then likewise, your y's can run from 0 to 12. What's the probability that y is 0? What's the probability that y is 1, and up the line? Okay. So when you write it out for a definition, I'll write it off to the side, and then we'll come back to this. Okay. So when you want if you want the marginal distribution for x, and that's our notation that we would use for it, you're going to take the sum over all of the y's of f of x, y. Okay. And this should be your probability that your x really is equal to x. That's in the discrete case. If you're in the continuous case, you'll integrate over all of your y's with respect to y. Now that's going to be a density function, so it's not equal to the probability that you're actually equal to x. But it's the same concept. Notice that, in general, when you compute your marginal PDF or your marginal PMF, the other variable has to go away. Okay? Because I'm looking for the marginal for x would mean I need to sum up over all the possible y's. My answer can still involve an x. It could depend on the x, but it can't depend on the y at all. Okay? Because we're adding it up or integrating over all the y's. Okay. Likewise, if you do your marginal PMF for y, you'll sum or integrate over all the possible x's. So if you do f sub y of little y, in the discrete case, that gives you the probability that y is equal to y. In the continuous case, you'll integrate over all your x's. Okay. So again, these are your marginal PMFs or PDFs if we're talking about continuous. Okay. All right. So let's go back to the picture and do this on the picture, and then we'll do it more generally as we get explicit functions given to us. Okay. All right. Going back to the picture here again, let's do the x's first because let's make sure it makes sense in our brain for what we can just look at x and look at its distribution, right? X again here is just a number that's selected from the set 0, 2, 4, 6, 8. What should be the PMF for that particular distribution? 1/5 for each value, right? Now let's do it according to the definition for the marginal PMF. It says for each of these values, we should sum up over all the possibilities for y. But look at how they're stacked. How many dots do we have over each one? 5, and each dot has a probability of 1/25. So if I add those up, I really do get a fifth, right? This is why they refer to it as a marginal PMF, by the way. We end up, if we want to draw it with a picture, we write the probabilities in the margin. So I would write a 1/5 here, a 1/5 here, a 1/5 here, a 1/5 here, and a 1/5 here. That's why they call them marginal. because when people first started making a development of this stuff, they would write these probabilities in the margins. Okay. We'll do the same thing for the y's, but notice your y's are a little bit different, right? That's not uniform, is it, for the y? Well, for the y's, we'll add a cross. So looking at y equal to 0, we would have what? 1/25th. For y equal to 1, we also have 1/25th. But know what happens when we get up to 2? We have 2/25ths, and the next one is also 2/25ths. The next one becomes 3/25ths. The next one is just 2/25ths again. And then a 3. And a 2. I didn't leave myself a lot of room, did I? Well, I zoom. That might make it a little easier for me to write. And then a 2 for that one. The next one's a 3. The next two are 2s, and then the last ones are 1s. I should be able to check my answer, because what should all those add up to? 1, right? They should all add up to 1, correct? 1, 2, 4, 6, 9, 11, 14, 16, 19, 21, 23, 24, 25. That does add up to 1. Okay. That was not too bad, right? So we started off with this particular problem. That was not too bad. Okay. All right. But that's why we write the marginal, and it literally gives you a straightforward example of what you're doing to calculate the marginals, right? We're adding across this way to get the y's. I mean, we added down to get the x's too, and it really did match up with what we thought that the marginal or the PMF should be for x in this case. All right, last one. Independent. Let's think about how we check if something is independent. When we did independent events with back in when we first started learning about probability, when you did independent events, you did the probability of x and y, or a and b, as what? How did you rewrite it if they were independent? Yeah, it should be multiplication, right? It should be probability of x times probability of y, or probability of a times probability of b, right? Okay. Same concept here, right? We should be able to calculate probabilities through multiplication. Okay. All right. Well, let's look at this dot right here. The probability of that dot happening, that would be the probability that x is 0 and y is 0, right? We've already calculated that to be 1/25th. Is that the same as the multiplication here? No. Which is not equal to the probability that x is 0 times the probability that y is 0. Because you get 1 over 1/25 if you actually multiply those two things, right? Okay. So they're not independent, but let's see if we could have surmised that without actually doing any computations, and then we'll do our definition for two random variables being independent. Good question. The probability of the and has to be the product of the probabilities. And we'll write down the definition here in a second for random variables. Okay. How would I have known, even without doing anything, these could not be possibly be independent? Well, look at the sample space. There's values that can happen for y for certain values of x, but not others, right? They literally have to depend on it. In particular, the values you can get out for y literally depend on the value you got for x, don't they? Right? So they can't possibly be independent unless your sample space is rectangular, right? I have to have basically an equal chance for your x's happening as you do for your y's happening, kind of, right? If it's not rectangular, you really have some sort of dependency between the two. So first off, if it's not rectangular, they can't be independent. Now, just because it's rectangular doesn't mean that it is. But if your sample space is not rectangular, they're automatically dependent. Okay? But our general definition for independent, X and Y are independent random variables if their joint PMF or PDF, either or, is equal to the product of the marginal PDFs or PMFs. And again, note X and Y cannot, X and Y cannot be independent if the sample space is not rectangular. If it's not a rectangular sample space, that's an easy way to say they're dependent. Now again, the converse is not necessarily true. Just because they're rectangular does not guarantee that it's independent. Okay. So let's look at the next example. This next example, we've got a joint PMF given to us. A joint PMF given to us as a formula. They tell you that the possible x's that you could get are 1, 2, and 4, and the possible y values that you can use are 2, 4, and 8. But they also tell you that your x absolutely positively has to be less than or equal to the y. Okay. So is your sample space rectangular? No. Okay. Sample space is not rectangular. So are these independent or dependent? They're dependent by default, right? Now, the reason why I want to make a big deal out of this is because notice that this part right here, especially if you've had differential equations, you've done separable differential equations. If you've had differential equations, separable means that I can multiply by function of x, no y's, times function of y, no x's. And it sure as heck looks like I can do that here, right? And that's what it looks like also in your definition of independent, doesn't it? Okay. That only works if your sample space is rectangular, right? Because we're doing probabilities here. We're not trying to separate the PMF into two pieces, right? We're trying to think about this as probabilities. Now, if your sample space is rectangular, then they really do have the same effect. It really is like what you do for separable differential equations is the same idea as being independent random variables if your space is rectangular. Okay. I'm just trying to make a big deal out of it so you don't confuse the two between classes, right? This really does look like I've got function of x, no y's, times function of y, no x's, which is what you're used to for separable, but that's not the only thing that has to happen for independent for random variables. Okay, I just want you to be careful with that. Because notice, I literally can do that here, can't I? Split it up as function of x times function of y. But it's not independent because, again, it's not rectangular. And it doesn't work for the probabilities. Yes? It couldn't. Yeah, it wouldn't have any conditions on the x's and the y's like that, right? Yep, you could pick any. If this condition weren't here, if this condition were gone, it would be rectangular. All right. In any event, so if I look at my sample space, let's draw out the sample space and put in the probabilities associated with each one, and even though that's not what the problem's asking for. Let's do the same thing, same thing that the previous problem asked for. Let's draw the sample space. Let's assign probabilities to each point, and let's make the marginals. even though I don't need to do that for this problem what it's asking. Okay? All right, so again here, my x's can be 1, 2, 3, or 4. I'll just put the 3 in there even though there's no x's. X's can be 1, 2, or 4. My y's can be 2, 4, or 8. I will count up by 2s on my y's because I can. But my x's will be 1s here. Where should I put dots? What dots are possible according to the conditions they gave you?
1, 2.
Okay.
1, 4, and 1, 8.
Okay. 1, 2, 1, 4, and 1, 8. Where else? What y value is going to be associated with the x of 2? I think 2 also works. Yeah, 2 also works. So you have 2, 4, and 8. But for 4, we have to use 4 or 8, right? Right? I can't use 4, 2. Yes. 1, 2, 1, 4, 1, 8. And just going through it. No, I'm not adding. I'm doing ordered pairs. 1, 2, 1, 4, 1, 8. That's where the dots are coming from. The reason why we did it for the other one because y was representing the sum. The y was the sum. Here we just have a x and a y value that we're given. That was why the previous one we had to add. Okay. In this case, it's pairs by default because the y is just a value. Yeah. Yep. Okay. All right. Let's see if we can put the probabilities. What is the probability associated with the 0.12? 1/12. Good. Because I put in 1 for x and 2 for y. For 1, 4, it'll be 1/6. And the other one will be, for 1, 8, it'll be 1/3. For 2, 2, it'll be a 24th. And then it'll be a 12th and a 6th. And then for 8, 4, it'll be a 12th. And then for 4, 8. Try that again. For 4, 4, I'm sorry, that's 4, 4. I put in the wrong thing. For 4, 4, it'll be a 24th. And then for 4, 8, it'll be a 12th. My apologies. Again, if we add up all of those values, what should we get? 1, right? So we can check. I'll just convert everything to 24ths. That's 1 plus 2 gives me 3, plus 4 gives me 7, plus 2 gives me 9, 10, 12, 14. Where was that? Somewhere along the line. Let's try that again. 1 and 2 gives me 3, plus 4 gives me 7, 9, 10, 12, 16 and 8. There we go. That's where it was added. 16 and 8 gives me 24. Okay. So I really do get 1 if I add those fractions all together. Are we okay with how we got that set up? Literally just putting in the x's and y's to get the probabilities? Yes. Just put in the x and the y value and compute the function. For each ordered pair. I got 1, 2, 1, 4, 1, 8, 2, 2, 2, 4, 2, 8, 4, 4, 4, 8. For each ordered pair. To get the marginals, again, we just add down to get the x's and add across to get the y's, right? So for the marginal for the x, we would add down. I've got 4 12ths plus 2 12ths plus 1 12th gives me 7 12ths here. 1 6 plus 1 12th plus 1 24th. That's 4 plus 2 plus 1. That's 7 24ths here. And then I've got 2 24ths plus a 24th gives me 3 24ths or an 1/8. And again, if I add across that, I better get 1. It's good ways to check your arithmetic, right? Because remember, again, to get the marginals for each individual x value, you add all the possible across all the possible y's. Do the same thing across for the y's. You would get an 1/8 here. You get, again, for 24ths, you should get 7/24 here. And you should get, 7/12 here. Now notice that your PMFs look almost identical, don't they? We have 3 values associated to each of the marginal PMFs, right? And they're the same values. So again, you might be tempted to think they're independent, right? But again, these are probabilities. Notice the probabilities associated with this point right here is 1/12. If I multiply 7/24 times 7/24, I don't get a 12. Right? So it doesn't fit the definition. Again, we already noticed that they couldn't possibly be independent because it's not rectangular. Okay? But just again to verify, this is x equal to 2, this is y equal to 4. The probability that x is 2 and y is 4, if it's independent, should be the product of those two things, and it's not. Okay. All right. So let's see if we can actually answer the question that we're being asked. What's the probability that x plus y over 2 is less than or equal to 5? So I need to pick an x value and pick a y value that satisfies that condition, right? We agree? Okay. So let's just go through. If x is 1, what y values can you use to satisfy that condition? I can use 2 works, I can use 4, and I can use the 8, right? Because this is less than or equal to, right? So I will know this will be 7/12 plus something, right? Because I can use any of the ones associated with 1. How about if I go over to 2? What can I use? I can use 2 and I can use 4, but I can't use 8 in that case, right? So in that case, I would have 1/24 plus a 12th, which is an 1/8, but either of those two. If I come over here to the last one, if I have x is 4, y equal to 2 doesn't even work. It's not in the sample space, right? Can I use 4? No, and I can't use 8, right? So these are the only values that I can have. You get what? 8/12, which is 16, 17 over 24 when I'm done. Yes. Oh, I got 1 out of 24, 1 out of 12. X is 2 and y is 2 works. So that gives me 1/24. And x is 2 and y is 4 works. So that was where I got the 12. Two plus 4 is not less than or equal to 5. And that doesn't satisfy my condition. Another way we could have thought about this from the picture, which will also help us when we get to continuous distributions. I want x plus y is less than, x plus y over 2 is less than or equal to 5, right? I could rewrite this as y is less than or equal to 2x plus 10, right? If I put it in y-intercept form, or slope-intercept form, I mean. Negative 2x plus 10. Sorry, forgot to subtract my x, right? We agree with that? Okay. Here would be x is equal to, y is equal to 10. That would be a y-intercept of 10, right?
And then if I do negative 2x, that would be an x-intercept of 5. Yeah. And then if I draw the line, they should go through that point. If I draw the line, I want everything at that line or below, don't I? We agree with that? I want everything at that line or below. So I would have basically those 5 dots. Yes. What's that? I'm drawing it from the picture. I just converted my inequality to that line, right? So I'm just having a linear inequality, and we're looking below this line. This is going to help us for continuous distributions. It's the only reason why I drew it in there. Okay. It's going to be very important to be able to visualize this stuff in continuous distributions. Why do you think I'm doing this? How did we say we were going to do probabilities for continuous joint probability distributions? Double integrals. Remember doing your double integrals? You have to integrate over a region. That's why I'm just drawing the picture here. Okay. All right. Let's see if we can do one like that. Oh, here we go. Okay. Here's one that's joint PDF, joint continuous probability distribution here. Okay. Hey, tell us that my f of x, y is x plus y, where my x's run from 0 to 1 and my y's run from 0 to 1. Now, is your sample space rectangular here? Yes. Okay. This is important though. Just because it's rectangular, does that mean they're independent? No. Okay. In particular, remember, independence says that I have to be able to write my PDF as function of x no y's times function of y's no x's, right? It has to be the product of the marginals. Looking at x plus y, am I ever going to get that as function of x no y's times function of y no x's? Is that even going to be possible? No. Okay. Let's see why, though. Okay. When we compute the marginals, it's using an F1 and an F2. Let's just call this an f of x and an f sub y here. Okay. Even though I copied these problems from an old edition of the book, it's changed notations from editions. Okay. All right. So if I want the marginal of the x's, remember that's the integrals over all the possible y's. Okay. Whoa. Shook the whole screen. All right. Now, now this is also important. As you know from doing double integral stuff, your limits of integration may be variables depending on what the region looks like, right? And that's also possible for when you're doing these marginals. However, we're integrating with respect to y. The y's have to go away. You can have x's left, but not y's when we do this, right? That's going to be different when we do conditional distributions next time. Okay. But for right now, when I integrate this, since I'm looking at the marginal, I can't have any y's left over, right? So it's possible that these limits could have an x in it. They don't have to, but it's possible, right? If your space is not rectangular, you might have x's here. Okay? And we'll see an example of that later. However, this space is rectangular, so what do your y's run from? 0 to 1. We're integrating with respect to y, so we'll get xy plus y squared over 2. Evaluated from 0 to 1, 0 to 1. These numbers are going in for y, not x, right? So when we're done, we get x plus a half. Of course, looking at the symmetry of this problem, what are you going to end up with for your marginal for your x, or your y, I mean? Maybe y plus a half, good. Yes. Why would I use a summation when it's a continuous distribution? The range is telling us that it's continuous. Yeah. Now, certainly we can tell that if I take my marginal for x and my marginal for y and multiply them, I'm not going to get x plus y, right? Which is the condition for being independent, is that the joint PDF has to be the product of the marginals, which we're not going to get here, which is what the problem's asking you to do. All right, let's see if we can do the other ones. When we defined the mean, back when we first defined mean, how did we define it? What is the definition of it? Expected value, right? It's expected value of x, right? Same definition. Remember when we do expected values, you do the function times the PDF and then sum it up over your entire sample space, right? That's what we do, isn't it? Okay. So in this one, we will integrate over the entire sample space. That's not too hard in this case because our sample space is rectangular. So I would do 0 to 1 to 0 to 1. And I'll do x times x plus y. Oops. dy dx or dx dy, doesn't matter. This would be our general definition for the mean of the joint distribution, or the mean for the x using the joint distribution. But of course, we could have also just done it like we did before, right? We have the marginal now for x, don't we? So I could just do that the same as what we did before. Just multiply that times the x and integrate from 0 to 1. You do the exact same thing, right? That's not any different. This is the definition, though, okay? But I'll go through it. This would be, I need to distribute my x through. X times x gives me x squared. I'm integrating with respect to y, so I would have x squared y, and then plus xy squared over 2. Notice now we're integrating over 0 to 1 of x squared plus x over 2. And this is what I was just mentioning a minute ago. Isn't this x times the marginal? Yeah. I could have just done it that way to start with. I didn't need to do this extra bit of work here. I've already done half the work already, right? I found the marginal. All right. This now we integrate. We would get x cubed over 3 plus x squared over 4. A third plus a fourth is 7/12. And that would be the mean. Again, by symmetry, you can probably figure out what the y mean is. Yeah, 7/12. Yeah, good. So you should be able to check that. It's very symmetric here, right? To connect this to physical ideas, if you will. This would be your sample space, right? If everything were uniform, what would your means be? If we were uniform in the x direction and the y direction, where would your means be? Be a half and a half, right? It'd be right directly in the middle, right? That's not what's happening here, though, right? As your x gets bigger and as your y gets bigger, it gets more weight, right? So instead of being in the middle, you're being pulled a little bit, right? And if you've done centroids before, that's what the same thing. right? Your mean of the probability that the mean of your x and the mean of your y are giving you the centers of mass for the x and the y direction here. Okay. So this would also correspond to the centroid of that region, given this density, right? The density is getting bigger as you move to the right, and the density bigger, heavy, whatever you want to call it. The density is more as you go to the right and as you go up. So it's pulling the mean both right and up. So the balancing point would be a little bit off to the right and up. All right. For variance, again, just to remind, your actual honest to goodness definition of variance is what? The expectation of what? Yeah, the x minus the mean squared, right? That's the actual definition, correct? Our working formula is still this. I'm not going to go through the computation because you should be able to do it, right? You've done these again, haven't you? And you do the same thing for the y's. But it's the same exact definition. We're going to get a new definition, hopefully here in a little bit when we start talking about what's referred to as covariance. Questions on that one at all? Yeah.
Yeah, that'd be more. Can you go through, or can you show why x and y
Are dependent?
Yeah, so
Okay.
that last step.
Yeah, so again, we would take, if I do my marginal for the x and my marginal for the y, I would multiply them together and get this mess. And that's not x plus y, which is your joint. Yeah. That's the reason why it's not. That okay? Okay. Pardon me. Let's look at the next one. See what we got. This one is not unlike what we just talked about for the original one. Let's not bother with plotting the points. It just literally wants what's the probability function for the single random variable u, which is defined in terms of x and y. Well, first, let's identify what the sample space of u is. What possible values can you take on? Okay.
4,
Yep.
5, 6.
Good. If x is 1, 2, or 3, and y is 2 or 3, then that's the possible values, right? So let's just go through. If I want, I'll call it f sub u, just to give it a different letter here. Oops, not 1. The possible values were 3, 4, 5, or 6. How can you get a sum of 3? Yeah, it has to be x equals 1 and y equals 2. It's the only possibility, isn't it? What is the probability that x is 1 and y is 2? Not 1/36. It's just the 1/6, right? It's just the 1/6 there because there's only 6 possible order pairs, right? I can use 1, 2, 1, 3, 2, 2, 2, 3, or 3, 2, 3, 3. Each of them has an equal possibility of happening. They're all 1/6. Okay. So in this case, it would just be 1/6. How can you get a sum of 4?
X is 1, y is 3.
Okay. X is 1 and y is 3. Or they're both 2. Yeah. Those are mutually exclusive cases, right? X is 3 and Y, excuse me, X is 1 and Y is 3, or X is 2 and Y is 2. They'll both have a 1/6, though it would have a 1. Whoa, that happened. So I'd have a 6th plus a 6th equals a 3rd. How can you get 5? 2 and 3 or 3 and 2, so that probability would also be 1/3. And finally, how can you get 6? 3 and 3, which would give you just a 1/6. These all better add up to what when I'm done? 1. And I do get 1 here. Yeah. So notice we've defined a new random variable in terms of 2 other ones and added them together. This is more, not so that the problem was super interesting in and of itself, but this is a precursor to stuff we're going to do in chapter 5. When we start defining new variables from basically doing transformations of other variables. Yeah, Kevin. The X and the Y here are independent, yes. Not because of the work we did, though. It's because the marginal PDF or PMF for X would be a 3rd, and the marginal PMF for Y would be a 1/2, and then a 1/2 times a 3rd is a 6th. It's not just that the space is rectangular, right? It's the space is rectangular and the joint PMF is the product of the marginals. So I'd still have to compute the marginals. Not that they're that difficult in this case, but you would still have to do it and multiply them together. Right. Yeah.
This might be like kind of dumb, but how does that answer what the probability function of U is? You just like count the probabilities of each.
That is the probability function. That's what it's asking.
Okay.
It literally just says what's the PDF or PMF, and that's giving you those. Yeah. I just didn't have an explicit function for it. The only way I could write it is literally that way. Okay. I just didn't write it. I could write it as a piecewise function, but it's not very interesting. I was just going to write out the values that way. The rest of the time, it's of course 0. Okay. Let's do the next one because it gives us a little bit of a sampling of our writing things as a double integral. In this case, we've got a continuous random variables for x and y. I don't know what the k is. So how are we gonna? What do we need to set up in order to figure out what the k is? Yeah, the double integral over whatever the sample space is of our PDF has to be, our joint PDF has to equal 1. All right, so let's think about what our space looks like. Certainly the biggest x or y we could possibly get is 1. I've got something going on where it says the x coordinate has to be less than the y coordinate, right? Well, where they're equal is on that diagonal line, correct? And since the x has to be less than the y, which side should I shade, above or below? If the x has to be less than the y. Or the y has to be greater than the x. Which side should I shade? Above or below that dashed line? Oh. It better be above it, right? That's where the x's are above. Or the x's are less than the y's. All right. Looking at that, how do you want to set up your double integral? I guess I should technically say iterated integral at this point. Okay, so 0 to 1 for the y's, and then 0 to y for the x's. So you're integrating with respect to x first and holding the y constant. So if I think about it this way, we're going that way, right? So then your left curve is 0 and your right curve is y. If you were going to do it the other way around, just for practice, just to remind, I know it might be been a minute or two since you've done double integrals. If I wanted to do y first and then x, what would your bounds be? The outer bounds are still 0 to 1 because that's what the x's run through. X to 1, right? Because you would be going this way, right? Holding the x constant, integrating with respect to the y first. So you would go from x to 1. Remember, when you integrate with respect to y, first you hold the x constant and look at a single x value. What's going on? It goes from the x up to the 1 versus the other way around. It goes from 0 to y. Like I said, it's been a minute, hasn't it? Okay. All right. This one's probably a little bit nicer, going from 0 to y, so let's do that one. You should get the same answer either way, by the way. Antiderivative with respect to x is kx squared y squared over 2, evaluated from 0 to y. When I plug in y for x, I get y to the 4th on top times that k over 2. I don't know, I keep putting equal signs on the left-hand side. So then we get ky to the 5th over 10, evaluated from 0 to 1. So what does the k have to be when you're done? It better be 10, yeah. What questions do you have? See if we can do one more here. 11's the same kind of idea. It just has improper integrals. By the way, I'm not going to do this one. I'll leave it for you. But looking at this one, are x and y independent? Try the other answer. Yeah, they are. Is your space rectangular? Yes, right? Your x's go from 1 to infinity, your y's go from 1 to infinity. So that's a rectangle, infinitely long on each side, but it is a rectangle. And also notice here that I can split up this as function of x, no y's, and function of y, no x's. So this really is going to be independent when you're done. Okay. You may have to split up your constant in a way where you get your marginals, but this really will be independent. Okay. So if you have a rectangular space and you can separate your variables like you do in diffq, they really are independent at that point. Okay. All right. Let's look at this one, because this one's a little bit more interesting of actually calculating a probability. Before I ask again, using that same idea, is this independent? Are these two variables going to be independent in this case? Yeah, they will be. You can check with your definition, calculate the marginals, and multiply them together. But space is rectangular, and I can separate my x's from my y's. It really will be independent. Okay. You may have to play with the constant. I'm not saying that. I'm not saying, absolutely not saying that your marginal for x is x and your marginal for y is y. Okay? Absolutely not saying that. All right? But it's the same kind of concept. Okay. So let's see what we can do here. Pardon me. Goodness gracious. Let's look at this part here. It's asking you for the probability that the y value is in between the x over 2 and the x. So again, like you do in calculus, it's important to draw your pictures. At least I think it's important to draw your pictures. Okay. All right, so your x's go 0 to 2. Your y goes 0 to 1. So your sample space really is that rectangle. Now let's draw in your lines. The line y equals x is that one, right? And your line y equals x, I'll just draw it over here, y equals x. Your line y equals x over 2 x over 2 is that one. And we want y to be in between those two values. So if I shade, it's that region. I know my other line doesn't look particularly straight. Are we okay with the region? Okay. To calculate the probability that you land in that region, I want to integrate over that region. Right? Okay. Do I want to hold y constant and integrate with respect to x first, or hold x constant and integrate with respect to y first? The way this region is set up. If I do x constant and y first, I would be going this way. And I probably want to go the other way, don't I? Because that way I keep the same bounding curves, right? Okay. So I want to do my integral. Oops. Change back to black. I want to do my integral of my PDF. I want to hold y constant first and integrate with respect to x, and then do the y's, right? I want to go this way because that gives me the same left and right bounding curve all the way for my x or for my y's, doesn't it? We agree? Okay. That makes your outer limits easy. What are your outer limits? Yeah, 0 to 1, right? Because they're the y values. Now the x limits have to be in terms of y, right? What's your lower limit? What's your upper limit? 2y. Good. Everybody okay with the setup? Like I said, I know it's been a minute since you've set these up. Okay. Antiderivative with respect to x will be x squared y over 2. Put in 2y for x, you're going to get a 4y squared. Excuse me, try that again. You're going to get a 4y cubed. And then you'll put in a y, you'll just get a y cubed. So we're going to end up with 3y cubed over 2. And then at that point, that should be a fairly straightforward one to anti-differentiate. You get 3/8. By the way, again, you should make sure that your answer makes sense. It's a probability, so it better be between 0 and 1, right? We're done. Okay? All right.
Is there a way to split the integrals up like at the beginning so the x's are on one and the y's are on the other? Or is that anything that they added?
You mean to try to write it as two integrals together? You can if I can pull the y out of this integral because it would be a constant with respect to the integral. But I can't really write it as a product of two things when I've got variables in my limits. if I go to the previous example, if I were trying to figure out this k, say I had that set up this way. Notice in this case, I've got a product of two functions. One only has x's and one only has y's. And I've got constants on both of them. Then I can break it up into an integral with, I'll pull the k all the way out because it really doesn't matter. I can do this as an integral with respect to x, and then times an integral with respect to y, that way. I can split it up as a product that way, but if that only works because I have two things going for me, I can split my x's and y's as a product, and this is rectangular. If it's not rectangular, I can't do that. I mean, if you can, it speeds things up, but in a lot of them, you can't do it. Okay. All right. Yep, you're welcome. Yeah, that's a good question. Thank you. All right. Let's just set this last one up so that we can get just get another example of everything being set up here. They give you a joint PMF. The x and y are both representing losses. Doesn't matter what the losses are for, they're just both representing losses. We want the probability that the total loss is at least 1. So in terms of x and y, what probability do we want? Yeah, the x plus y is greater than or equal to 1. Okay. So again, just like the previous problem, I think it's helpful to draw the picture. My x's go from 0 to 1. My y's go from 0 to 2. So my sample space is that rectangle. Same kind of problem, just my rectangle's been turned 90 degrees. Okay. Same idea. We want to graph this inequality. If I think about it as y is greater than or equal to negative x plus 1, then I'm looking at that line. I missed my x-intercept. Pretend like that goes to x equal to 1. Do I want to shade above or below? Above, yeah, because we want the y to be bigger, right? So I want that region. Now, if I hold y constant and integrate with respect to x first, I'd have to express it as two integrals, right? Because my left bounding curve would change. If I express it the other way, if I do x first and then y first and then x, hold x constant, I've got the same bounding curve on top and bottom. One of them will be 1 minus x, and the other one will be a 2 for the y's, right? However, you may notice, at least I might notice, and hopefully you do too, that triangle that I just colored in blue is a little bit easier to describe, isn't it? How could I use that triangle to get me the probability that I want? Yeah, do the complement. Yeah, exactly. Do 1 minus. Good. So this would be 1 minus the integral of my PDF. Let's do dy dx. Hold x constant first. What will your limits be for the y's? For the y's, it'll be 0 to 1 minus x, and then for your x's, it'll be 0 to 1. Because this is the line y equals 1 minus x. Literally the only reason why I did it that way is because I like to have a limit of 0 if I can for my integral, because it makes things a little bit easier. Okay. If you did it the other way, you go get the same answer. It'll just take a little longer to get there, right? So if I can write it in terms of something that has a limit of 0 in it, it just makes my life a little bit simpler. That's okay? All right. We'll do more of these next time. I was hoping to get a little farther today. What I would like you to do, and I haven't asked you to do this for a while, there's a video on Moodle titled The Correlation Coefficient. Okay. Please watch that for Thursday before class. We're going to talk about covariance and correlation next time. What I go through in that video is the derivation of the least squares line, and I don't want to necessarily take up the time of class to do it. So, but I do want you to be familiar with least squares line, because one of the more important types of approximations you do for data sets. So watch the video called The Correlation Coefficient for Thursday. You also have homework due on Thursday. So, all right. Have a good one. We'll see you then, if not before.